Good morning, everybody. So I got the privilege, because Zach, I think actually wanted to not do it. No, I'm just joking. But he gave it the privilege to introduce Leo. Leo is someone who needs very little introduction. He has built some of the most impactful tools in formal methods, automated reasoning. Many of you have used them, Z3 and now Lean for much of the last decade. On top of being an extremely talented programmer and really pushing the state of systems in this world, Leo's also been a great mentor and community figure. I remember when I was a second-year grad student, I was working on my own proof assistant, which didn't last very long. And I met Leo, and he just encouraged me to come work with him, and really many other people in the audience who are now working the Lean team, kind of, even though we had very little experience doing this stuff, helped us grow into new researchers and build some really great stuff. And so I think not only does he represent the technical part of the community, but also the social good part as well. And with that, I'll let Leo take it away.
Thank you, Jared. So happy to be here. Let's see if I can get my computer home again. Hi, everybody. I want to get you excited about Lean. Today is a really special day for me because Jared is here, he contributes to Lean. But also Sunho that I started Lean with is here, Sebastian Ulrich that is a co-founder of the Lean Flow with me, Gabriel that contributes to Lean for so many years, they're all here, it's a special day. Okay, Lean, the beginning of the project was all about software and hardware verification, right? We all want verified systems, right? We want these systems to behave as we expect, right? We want every proof for correctness we want to be able to check them independently with external checkers. That was the origin of the project. But before Lean, there was Z3. Z3 is a state-of-the-art SMT solver. It has been very successful at Microsoft at bug finding, right? Microsoft Sage by Patrice Godefroy caught so many bugs at Microsoft, right? Patrice has so many good statistics showing the number of critical failures, security vulnerabilities decreased dramatically after Sage. But on the other hand, program verification was always a part that was tough. We had so many unhappy users in software verification. I remember Nick complaining about Lean. Nick is here today, a great former colleague. He would complain about Z3 many times to us, to Nikolai and me. People using Daphne would also complain. And the problem is undecidable. It's really hard to have a push button tool that will work when the complexity goes over a specific threshold. And Lean started with the goal of addressing this hole we had, right? We want to have a tool that would have the best of interactive and automated theorem proving. Lean today is an open source programming language and proof assistant, right? One thing that was unexpected, we never planned in the beginning collaboration was not even in our radar. But many of the math folks that use Lean, they say the main thing is collaboration for them. It enabled them to collaborate with people they never met. These are recurrent messages we receive from our user base. Lean tooling, all the tooling in Lean is implemented in Lean, right? Lean is very extensible. If there's one thing I want you to take away from this talk, is Lean is extensible and you can make it your own, right? The math community did it, and we have many other examples of people that made Lean their own. They built their own system inside of Lean. And Sebastian and I, we are really proud of our tooling is all implemented in Lean. The LSP server, the parser, the macro system, the elaborator, the type checker, and so on, they're all implemented in Lean. And Lean has a small trusted code base. At the beginning, it felt like all proof assistants, all major proof assistants, Isabel, Rock, Agda, well, not Agda doesn't have a small trusted core, but many proof assistants have a small trusted core. At the beginning, Fuzzy said, oh, we have to do it too. And we had many soundless bugs in the passing in Z3. It felt like a good idea to have a small trusted core from the beginning. But we didn't see, one thing that we didn't expect, that many people that are excited about AI today, they care a lot about the small trusted core, right? They know the AI can exploit and will exploit any soundness bug in your tool, right? They are trying to increase, they have a goal, they want to achieve the goal. If using unsoundness is the best way, they will do it, right? And now, for many, I mean, Lean started 12 years ago, but 2 years ago, Sebastian Ulrich and I launched the Lean Flow. That's a non-profit dedicated to the development of Lean. From the beginning, right, Lean was based on dependence type theory, right? We were studying many of the different approaches, and one thing we wanted a system that would be great for math. Our first user was Jeremy Avigad. He's a mathematician, and he made this point over and over again that in abstract math, you need to manipulate many objects like groups, rings, fields, and they all should be first-class citizens. You should manipulate them as objects in your language, right? And there's no other way around. Of course, some people would say, oh yes, you can use this crazy encoding, but we do not want our users to be distracted with encoding tricks. So people that claim that you can use a fancy encoding is the same people that would say, oh, you can program anything in a Turing machine. Who is going to do that? Nobody, right? You want to work at the right level of abstraction. We wanted to enable our users to focus on the math, not on encoding tricks. Here's an example from Kim Morrison. Kim has been contributing to Lean for 10 years. He works with us at the Lean Flow. And here, Kim defined an example that's going to be in our manual. Index map is a mapping from alpha to beta that you remember the order things have been added, inserted into the map. The map here, the first thing you see, the first feature in the first line, Lean has type classes. The alpha should have a Boolean equality, is this BEQ, and should also have a hash function. That's what it means to be hashable, right? Then you have 3 fields that are data, indices, keys, and values, right? And the 2 last fields are propositions you can view as invariants that any element of this structure should satisfy, right? The first one is that the arrays keys and values have the same size. And that's why we call it dependence type theory. The type of these fields depends on the previous fields. That's why it's called dependence. And Lean here, you can also, when you define a field, you can tell Lean the default way to synthesize values of these fields. If it's not provided, what you should do. In this case, to call a proof of automation called grinds, right? And the same thing for the well formulas field. It's basically saying that for every integer, every natural number I, right? If there is a value at position I in the keys array, then this value, the indices map this value A back to I, right? They are saying one is the inverse of the other, right? And again, if this field is not provided manually, a proof will be synthesized. Lean will try to synthesize the proof automatically using grinds, right? It can be any tactic, right? Any piece of proof automation you want. In this case, you're saying it's going to be grinds, right? The full example is here. The slides are available online. You have the link at the end, but you can see the whole example here. And then Kim defines the insertion function, right? The insertion requires an extra property, that's the alpha. The Boolean equality is not just a function, a binary function to a Boolean, but is also lawful. What it means is it returns true. The elements are indeed equal to each other, right? So you cannot return false everywhere, for example. And then it proceeds as follows. You check the hash map indices. If the element is there, there is a value I there. You just update. Otherwise, you insert the new elements, right? And you see the two fields have not been provided at all. The proofs have been synthesized. The code looks like a regular code that you would write in a language like OCaml, but the proofs, the invariance, Lean's proving behind the scenes. If you want, you can prove yourself manually, provide the proof term. If the automation does not work, you can provide the proof yourself. But by default, Lean will try to synthesize the proofs automatically for you. And as an example, Kim tried to make the point here that there is a difference between library building time and library usage time. Right? Some annotations it provides for the proof automation are local, are used just during library developments when they were developing this module. Right? After they are done, you can expose to the users the theorems they want to use when using this mapping in their own programs, right? So here you have 4 main theorems that you are going to use, and all proofs were done automatically using grinds. Theorems in Lean are like definitions. As any other dependently typed theory, there's no real distinction between proofs are terms, right? Types, propositions are types, right? The same thing is true in Lean. The only difference in Lean is that when you say something's a theorem, the system will enforce the resulting type to be a proposition, right? Otherwise, you will reject. Okay, another thing, people ask us over and over again, what's the secret? Why Lean is successful? For us, one thing that we really do is listen to our users. Lean has good support for classical mathematics from day one. Right? Our first user was a mathematician, was Jeremy Avigad. The math community using Lean is growing rapidly. They love the system. I remember Clark Barrett told me a few weeks ago, he's a professor at Stanford, saying, wow, one thing that blows my mind is that every single Lean user I meet, they love the system. Right? And making sure for math, the math folks, constructive mathematics is a completely alien thing. None of them don't even, advanced math, you cannot even write, you would have to rebuild so many things from the ground up to be able to do the math they're doing using constructive principles. They do not care about that. They want to operate the way they operate. All Fields medalists today use classical mathematics, right? And Lean has great support for that. Also, another thing, it's funny that people like Kevin Buzzard, Terence Tao, they come to me saying, oh, you computer scientists, only you are constructivists. This is not true. Most computer scientists couldn't care less, right? Developers don't even know, most developers don't even know what constructivism is. And verification engineers, they only want to get the job done, right? They want to finish the proof, right? They don't care if the proof is constructive, is classical, they want to get the job done. MathLib. MathLib is the Lean mathematical library, right? It's a project with over 500 contributors. It's reaching 2 million lines of code. It has more than 100,000 theorems inside. In 2020, we had this article in the Quanta magazine. There are many really nice codes. My favorites from Heather Macbeth, when she says she's investing time because in the future, she wants people to have an amazing experience. And yeah, she predicts the future. Many people benefit from MathLib. We like to say that Lean is a development environment for formal verification, right? It has a rich user interface and integrated tooling, right? The tooling, we have a build system that's called Lake. It's Lean Make, it's a funny joke. And he's our Cargo, right? It's inspired by Cargo. And okay, since it's called Lake, the build system, okay, Rust called their package crates.io, ours is a reservoir, right? And the environment provides runtime feedback, real-time feedback, errors, goals, hints, and so on. And it's funny that Jared did the introduction today because he insisted from the beginning. He actually was really annoying in the beginning, saying, we need to have great tooling, we need to have great tooling is essential. He was right, but it was annoying. At the time, we would have bare bones things. And Jared kept insisting we needed great tooling. It took many years to get great tooling. But he was right. It's super important for our users to have great tooling. And here is the Visual Studio codes interface. That's the favorite used by the Lean users. Vim is the second. I mean, there are many math folks that use Vim. The interface with Lean is also really great in Vim. But in VS Code is getting better and better, right? Mark Huizinga, he works full time to provide a great experience to our users. You can click anywhere in a Lean proof on the right hand side. Can be even a different monitor. I mean, Mark spent time making sure this works smoothly. You have the info view. And this is not a static object, it's interactive. You can hover and get extra information about anything there, right? For example, I don't know what M prime is. I would say, oh, M prime is a submodule of M. Oh, I don't know what a submodule is. Lean will keep jumping to the definition, right? And you can keep going. I mean, I don't know, a submodule uses an additive submonoid. I don't know what it is. You can keep jumping. That's one thing that Kevin Bussard would say. With Lean, if you want, you can keep zooming in until you go back to the axioms of mathematics. And when he starts using Lean, that's one thing that got him really excited. He would say, math is data now, you can transform it, right? And the same infrastructure that we have in VS Code is also used for a documentation outreach system called Verso. It was built by David Christensen, and Verso, all the documentation is interactive, right? And uses the same infrastructure. We call it, since everything is integrated in Lean, we claim that we have flywheel improvements to any of the pieces help each other and provide a better experience to our users. Let's focus a little bit on mathematics now. I mean, that's how Lean became popular. Today, it's mind-blowing to us. I mean, sometimes Sebastian and I feel like we don't believe it's true. But we were joking a few weeks ago that we managed to get the greatest living mathematician recording YouTube videos online, showing him using Lean, right? And he keeps using Lean with different AIs. And for him, the main big deal in Lean is large-scale collaboration. He told me when first time I met him, I never imagined that one day in my life I would get a contribution from an amateur mathematician, right? I only work with the best, but now I get contributions from people that are not even mathematicians, even computer scientists contribute sometimes. And for him, this was mind-blowing. He doesn't have to check the contributions because he's checking with Lean. And he also envisions this kind of system as the future for math, because now he envisions a future where people are going to be interacting with AI. There will be humans and AI working together to solve really hard problems. And just by coincidence, this Saturday, they released a podcast with Lex Fridman. If you don't know, Lex Fridman is one of the most influential podcasters in the US. And he had a 3 hour and 40 minutes and 15 seconds to be the pie interview with Terry. And Terry spent more than 40 minutes talking about Lean. I mean, we're really happy. There are many other major projects today. Vermaele's Theorem by Kevin Bussard, that is massive. Nobody today understands. I think Kevin even claims that nobody ever fully understood the Vermaele's Theorem proof. People understand parts of it, not the whole thing. Having it formalized will make sure these results will survive, because Kevin believes people are dying. The few people that understand the pieces will die, and nobody will know the proof anymore, why it works. But how did we get here, right? Kevin had an instrumental role in our journey, right? In 2019, he said, we have to do modern mathematics, cutting edge math. Nobody cares about a result from the 70s. We have to formalize modern mathematics. And he decided to formalize perfectoid spaces. This is a mathematical object defined by Peter Schulze. Was not by accident. Peter Schulze got a Fields Medal in 2018, and Kevin said, okay, let's do it. I mean, let's see if Lean is powerful enough to formalize this object that is extremely complicated. They did not only succeed, but they learned important lessons. One of them is that math is data. You can produce a dependency graph automatically. Now that math data, you can refactor proofs using tooling. You can write tooling that analyze your data. All of that was news for the math folks. With the success of Perfectoid Spaces project, Peter Schulze himself, he challenged the community in 2020. He said he had a new result. He was obsessed about it in 2019. He was not sure about if it was correct or not. He felt like everything was correct, but nobody would dare. The complexity was so high that nobody would dare to check all the details, right? And I remember Kevin in December came to me saying, it's going to take years. We're going to do Kevin is like that. We're going to do anyway. Even if it takes years, we are going to do it, right? But to our surprise, a team led by Johan Komelin did it. The main result, the main crucial lemma that shows he was unsure about, they verified in a few months, right? He made the announcements, the main results. It was a big deal. I mean, they fixed many mistakes in the proof, all small ones, I mean, local things that can be easily fixed. And these results showed up in Nature. It's a big deal. Math results usually do not show up in Nature, right? But didn't stop there. I mean, for me, what was the most unbelievable thing they achieved is that they did not only verify the whole thing, but they simplified the proof without understanding the proof. Johan would tell me that he could see only 2 steps ahead. They replaced an object called the Brindleline complex. Don't ask me what it is, I don't know. But they replaced, for me, it's a data structure. They replaced this data structure called the Brindleline complex with a much simpler one. And the proof still goes through with the simpler one. They did a refactoring step in our terminology, using our terminology. And Johan was saying, Lean was a guide, right? He managed to do all these simplifications because there was an assistant next to him, helping him along the way. Then I read this, Peter wrote a blog post. I mean, it's unbelievable. I mean, he's a Fields medalist, but he wrote a blog post. There was a quote there. I said, come on, he did not write that. I mean, I started checking with Kevin. No, this was what Peter wrote, that Lean was really an assistant, helping him to navigate through this thick jungle the proof is, right? Basically, he was saying the object, he couldn't keep all the details in his head, right? This is one example that I was happy. Another example I was really happy is from Kim Morrison. Kim joined us in 2015, around 2015, the very beginning. I remember the beginning, I thought Kim was insane. I said, what this mathematician cares about Lean? The system is barely usable at this point. I thought they were nuts. I mean, but kept building. Kim is one of the founders of MathLib. And I remember the time he said, I'm working in quantum with one of your colleagues, Mike Friedman. Mike Friedman was leading the quantum team at Microsoft. He's also a Fields medalist. And one day he came to my office saying, Kim is the smartest person he knows. Yes, Kim is really smart. But recently, Kim formalized his paper, the results from his paper in Lean. And they told me that there was a bad taste in their mouth because when they published the paper, the results were checked with a computer algebra system. And for mathematicians, it's like blasphemy to have something that's an unverified computer algebra system checked. Feels like your result is not real because you needed this computer algebra system that people believe there are many bugs. But finally, we could check again the results. And here, one of the highlights is that we are reasoning at abstract math. You're saying is any commutative ring that have characteristic 0. This is not a toy. I mean, this example encodes real algebraic constraints derived from relationships among diagrams in a pivotal tensor category, and it can be checked in milliseconds in Lean. And Kim was excited because this was demonstrating now that we can finally explore mathematical and physical structures, like from topological quantum field theories to fusion categories, right? And the tooling is now finally good enough that you do not have to rely on computations done by hands or unverified computer algebra systems. And Kim, besides being a great mathematician, also assisting us building Lean itself. For example, this grind tactic, Kim is a key contributor to it. And also to making sure that our users are happy. A few weeks ago, for example, Terence Stahl wanted to reason about linear ordered vector spaces. You can use a variant of linear arithmetic, but it's not, you have to change. For example, you cannot use SMT solver here. SMT solver is a hard coder for integers, natural numbers, reals. Here you have something that's not a natural number or an integer, right? It's an ordered vector space. It's also not a commutative ring. That is usually the structure that most proof assistants build linear arithmetic on top of. It's a variance, and we made it to work to make sure our users are happy. Right? This is super important to make sure that we remove the roadblocks that allow them to scale. Right? Software. Let's use the second half. I want to use the second half to talk about software verification. Today, after this huge detour through math, Lean is used in many software verification projects. Right? You can write code in Lean and reason about it simultaneously. Right? You can prove your code as the properties you want. CIDR was the first project to use Lean at AWS. CIDR is a policy language. Right? They wrote a model of CIDR in Lean. A model that is executable, and they proved key properties about this model. Right? The setup is as follows. Right? CIDR that runs in production is implemented in Rust. Right? But they have a model written in Lean, and they prove many different properties about this model, and they use differential testing to show that the model and the code in production behave the same way. If there is a discrepancy, something will have to be fixed. And Minator led this project. For her, a big deal was the fact that Lean is fast. The model you can execute more. Actually, her experiments, her modeling Lean is faster than the production code in Rust, right? Enables them to verify many tests overnight. Another thing for her that was a big deal was maintenance. Maintaining the proofs before using Lean was a nightmare to keep the proofs maintained. They would break all the time when people would update the verification technology. Should spend weeks patching proofs. Now, minutes. She fixes everything when a new Lean version is released, right? If you want to learn more about Lean, you can check her blog posts. Kasia and Emina wrote a blog post in 2024, last year. You can read more about how Lean is used in their projects. SAMCERT, I will not tell you much. We had a talk yesterday about SAMCERT. It's an open source library for verified differential privacy. One thing I really like about this project is not the fact they verified, but they made it twice as fast. because now you could verify, you can implement aggressive optimizations without fearing the introduction of bugs, right? And I love this quote from Jean-Baptiste. Many of you know Jean-Baptiste contributed to CompCert, was a key figure in the CompCert project. And one of the quotes I love from him is that SAMCert would not exist without MathLib. Right? He told me he felt like a kid on a candy store. All the pieces he needed were there. He needed for analysis, number theory, topology, every single bit was there. He did that in record time. I mean, people that know Jean-Baptiste know that he's really smart, but I was blown away how quickly they managed to push this project forward. Since then, he learned to love the fact that Lean is a efficient programming language. And he pushed new projects like TensorFlow using Lean. Verified cryptography at Microsoft. This one is funny. When I met them, they said, "You silly, you just had to leave for us to start using Lean." I mean, now that you left, we are using Lean for verifying crypto. They had a blog post recently about Syncrypt, where they are modernizing their crypto libraries and porting them to Rust and verifying using a tool called Aeneas. Sonho developed Aeneas. He's now at Microsoft too. You're working with Jonathan Prochenko. And for them, one key differentiator was that the fact that Lean was extensible. They wrote their own proof automation, right? And also they relied on MathLib, right? For them, MathLib was a key asset. I remember Cedric is part of the team. I know Cedric for more than 20 years. Cedric's not the kind of person that compliments people, but he spends, last time I had dinner with him, several minutes praising MathLib. And I said, can I record you saying, could you say it again? And I record, because it was so nice. He's saying, MathLib gives me the results I need at the right level of abstraction, right? And their setup is a variant, a variant of what Cedar uses. Here they have the Rust code, but they use Aeneas to automatically translate the Rust code into Lean, and they verify the model that was automatically generated by Aeneas. The software engineers only touch Rust, and the proof engineers only touch Lean. Someone was telling me that he was using Aeneas and developing Aeneas and writing many extensions. I took a look, let's see what he's doing with Lean. I was blown away. He has lots and lots of extensions. I got a few examples just to highlight some of the features. For example, he defines his own static syntax. You see it's very elaborate. You have optional elements. The to is optional. You have an optional list of terms, and you have a location that's optional. And then he writes a function that's the handler, that's in our static M monads that we use to write statics in Lean. And you have pattern matching that Sebastian implemented, this pattern matching for syntax. It's not just, it works even for your own syntax. You can define new categories in Lean. We have expressions, you have commands, but you can define your own syntactic categories, and the pattern matcher will work. It's a great productivity tool. It's great to see it being used in this example. Another thing, it's not just that you're adding new statics. You can add extensions to the Lean simplifier. As any proof assistant, the term simplifier is a major working horse. And here's Sonho implemented his own simplifier extension and his own hook. I mean, in Lean you can attach, whenever you see some pattern, you can put a trigger to call some code that will simplify the term. Of course, you produce a new term, not just a new term, you have to generate a proof that it's equal to the inputs, right? And also another thing, evidence, a piece of evidence that we really care about our users. Sonho came to us, his proofs are gigantic, right? And at the time, Lean would have only parallelism it would basically go at the file level. You could compile many files in parallel, and when you change a proof, you should go to the beginning of the proof and process from there. For the math folks, this was good enough, but for Sonho was not. And Sebastian implemented many cool things, but this one is really cool, that you compile the whole lin file in parallel now. I have here an artificial example. I love to see this orange bar showing which all the parts that have been compiled in parallel by lin. And it's really fun when you are working, you see things moving, being proved completely automatically, all in parallel. And Sonho was really pleased that Sebastian implemented this feature for him. That's one message. I mean, Lean is extensible, and you really care about your users to get them using your system, right? This week, we had this nice surprise from Ilya and Vladimir demoed Veil to us. We were blown away. I mean, I remember when we were beginning Lean 4. I mean, Lean started in 2013, but we wrote it a few times. Lean 4 is the last one. The lesson is going to be the last. We're not going to start from scratch again. But when we started Lean 4, with all the lessons we learned, one thing Sebastian and I kept saying, we want people to define domain-specific languages inside of Lean. Right? You want them to be able to do that and leverage all the tooling, the proof automation we provide, the syntax. This is a Lean file. I even asked Ilya, this is a Lean file? I couldn't even recognize. He defined his own GSL, right? And everything, right, is being checked by Lean. He has bounded model checkers, he's calling SMT solvers. If the automation, the push button automation does not work, you can go back to interactive proving, right? I put a link to the website. You can also check their latest paper at CAV. They also have a separation logic framework for Lean. It's also in their GitHub repository. But if you care about protocol verification, a series of blog posts by Igor Konov is also, they are great. I mean, he's just learning Lean. We were really impressed. I mean, we learned from Mark Brucker. Mark Brucker is a vice president at Amazon. He really cares about protocol verification. And he sent me the first blog post saying, look, take a look at that. Igor, he defined a protocol that is two-phase commits in Lean, and he wrote a simulator. In Lean also, he wrote the protocol in Lean, wrote a simulator for the protocol. It's a generic simulator for like doing some kind of model checking in the protocol. And he was blown away that his simulator is faster than the model checker he was using before, right? It's not just faster, it's like a little bit faster. It's like, I think it's 168 times faster, right? And after that, he proved the protocol corrects in Lean. Of course, he's a new user. He doesn't know all the proof automation that's available, but it was quite impressive. He also proved its liveness properties. And I love this quote from him saying that no other interactive tier improver captured my attention for so long. I mean, he made our day. You know. KLR. KLR is another project at Amazon. It's part of the reference implementation for our neuron compiler for generating GPU codes. It's a project led by Daniel Cronin. He's here. You can learn more about it. But again, here, another highlight is that Sean is one of the main people pushing the project, developing. He put this code, he didn't send to me, it was in an open Slack channel at Amazon. He was blown away by the metaprogramming. He was saying metaprogramming is amazing. He managed to remove a lot of boilerplate codes. And these compilers have tons of boilerplates, and he could automate everything using Lean metaprogramming. I recall before joining Amazon, I was talking to Sebastian. We like to view as we design Formula One cars, but we need to find pilots. And Amazon has so many good pilots, like Emina, Jean-Baptiste, Sean is another one. They are amazing. And it's open source. You can check their codes online. And they use bit vector reasoning, right? Here, like this decoder here. And it's a good, I select this part because it's a good segue to another piece of automation we have in Lean that we are really proud of. Is BV Decide. BV Decide started, it was an epic battle to get everything. It started in 2023 with Josh Kloon. Josh Kloon was my intern at Amazon, and his project was to write a verified LRAT proof checker. LRAT is a format for produced by SAT solvers, right? It's optimized for SAT. Right? It's way more efficient in coding than you'd get if you were using proof terms that are available in Lean. And he wrote a checker in Lean. He verified this checker. The checker leverages many performance improvements we have in Lean, like many of you at PLDI are familiar Perseus. I mean, Dan Lyon had this paper a few years ago where he describes Perseus that use a technique similar to the one we have in Lean, in Coca. And this is the performance we get there is key. Perseus was key to deliver the performance we have in this proof checker. Again, is the flywheel. The fact that we have efficient code generator was key here. After that, Henrik Boving, he implemented a verified bit blast in Lean and a verified CNF translator. It's not just for bit vectors, also for finite types like scalar types, structures that only contains finite types. His BV Decide tactic can handle all that. And we use a very efficient set solver CAD call from Armin Biere, right? And this tactic is great. I mean, it's like a number crunching, right, thing. For example, let's see how we use it to verify pop counts. Pop counts is from this book, Hacker's Delight. It's this really obfuscated piece of code that you can compute the number of 2 bits in a bit vector, right, without using any loops, right? It's really mysterious piece of code. But then you have, on the right-hand side, you have pop spec, is the specification where we use a recursive function in Lean to count the number of bits. Another thing to highlight here is that on the left-hand side, you see we have imp is a GSL we created for this example. It's a GSL for this imperative language. It's embedded in Lean, you can write it, you can get syntax highlights, everything. And now you want to prove that the two coincide with each other, right? We wrote the theorem, and basically you use simp, the Lean simplifier. Simp here is exposing all abstractions, right? Reducing the problem to the language of bit vectors. After you have a problem that's only bit vectors, you call BV Decide and your proof is done. Here, the automation you see is surgical. We use simp to expose the abstractions. There's no guessing, you are telling exactly what we want to expose, and you get a bit vector problem, and you call BV Decide, and you are done. Another question we get all the time is, does Lean have hammers, right? Hammers are popular in proof assistance, right? Yes, the community is building that, actually true now, being actively developed. Lean Hammer at CMU is calling first order, not even first order, it supports a little bit of higher order logic, superposition. They do proof reconstruction in Lean. Lean Hammer is already available. And there's also Lean SMT from Stanford that invokes CBC5 and will also do proof reconstruction, right? And Clark has many students working on this project. Yeah, it's again, all of them are using extensibility. They're using the Lean metaprogramming, right, for doing the proof reconstruction. We saw BV decide as a tactic that reasons at the bit level for bit vectors. We saw that grind allows you to reason at higher levels of abstraction. For some bit vector problems, you can solve them using the fact that a bit vector is a commutative ring and has characteristic, in this case, since it's 16, 2 to the 16, right? And this equality holds always because 256 times 256 is 0 for a bit vector, right, of size 16. That's why this equality holds, and grind knows that, right? Here it's exploiting the fact bit vectors are commutative ring. There's no bit blasting going on. And grind also allows you to write programs in a very clean way, like the shift down from heap sorts. All these array accesses in Lean, you have to provide a proof that the indices are in bounds, right? And here this is all happening behind the scenes. And grind is not just arithmetic. It knows, for example, that swap. It knows that when you swap two elements of an array, the size is preserved. And this is key to finish. To not, if you grind did not know that, you would have to write these proofs manually. They would catch in your way, right? And to prove that shift down preserves the size of the array is also just a single line. You say use functional induction and then apply grind to each sub-goal. Functional induction is just an induction that abstracts the control flow of your procedure. Diagnostics. We like to say that proof automation is great when it works, but it's even more important for it to explain why something did not work, right? And in grind you have very detailed diagnostics information. For example, it will produce an assignment for the linear integer constraints. You can also see, you have many folders and you can open, which propositions grind knows to be false. It will tell you. It will also tell you matching instances. We heard a lot about matching during this PLDI. Matching is a technique for instantiating theorems, right? And sometimes you want to know, a recurrent problem is that you instantiate too many theorems and you're consuming a lot of memory. You want to know how many times each theorem was instantiated. You know, grind tells you exactly. You can diagnose what's going off, something that's off or is consuming too much memory, you will find out. And again, the flywheel again. This is using the same infrastructure we have for providing type information for terms is also here. Oh, you don't know, you don't remember what array gets lm set ne is? You hover, it will show you the type. You know exactly what is the type of this theorem. Okay, but what exactly is grind? Grind is inspired by SMT technology. You should view it as a virtual whiteboard where you are learning new facts and putting on the whiteboard the procedure. And there are many engines that cooperate to put more information on the whiteboard. And it works like every single SMT solver these days. You keep merging equivalence classes. And the engines are congruence closure, matching, constraint propagation, guided case analysis, and many solvers like linear integer, solvers for commutative rings, for linear arithmetic, but for abstract structures. It's unlike, differently from SMT solvers, it supports dependence type theory, right? You do not need to do any encoding trick. It works directly on your goal. It understands the type class mechanism. It understands dependent pattern matching. It can pattern match, do case analysis on match expressions, and it produces Lean proofs, right? What it is not, right? I think for us it's really important to set the expectations for our users. It's not a tool for doing massive case analysis, right? For this kind of search, you should use BVD size. If you're doing massive case analysis, your proof term is going to be gigantic, right? Especially if you represented it as a lean proof term, would be a huge waste. It's much for this kind of problem when you're doing massive case analysis. It's great to have a custom certificate for that, like we have in BVD size, using the LRAT formats. One key takeaway here is that if we view like, because we provide diagnostics in grinds, for us, if you see that your grind is going to performing a lot of case analysis, many case splits, the idea is that you are using it wrong, right? That's not how you should use it, and you should switch to a different tool. A few years ago, sometimes I think Kim is very competitive, but a few years ago, Ruslan Leno, Shankar, and Stefan Merz, they challenged the link. They created this challenge: if then else normalization procedure, like something that would normalize all if then else's in your in this data structure. Make sure they had many things. They provide a list of things that should be normalized. Ruslan approached me. I want to see you to solve this challenge. I didn't even try. I just posted on Zulip. In Lean, Zulip is the channel where the community gathers. We have really smart folks there on Zulip, really smart folks. They solve it in record time. I mean, people are blown away. These folks are really smart, but their solution was a really big manual proof, right? And Kim was not happy. Said, okay, I'm going to do it again. I mean, but using grinds. And did it. I mean, of course, I'm putting just the main function here. But all proofs are single liners, right? Again, the main results is he proves that the code respects the spec is one line, function induction followed by grinds, right? But you may say, oh, how do I find out that I have to use function induction? Actually, we have a tactic called try. Kim likes to tell users, you have to learn one to become choose Lean. Learn to use try question mark. You put try question mark, and Lean will tell you what works. You will try many different things. Hopefully, Sebastian one day will make it do in parallel. He told me he would do it, and you do it to run in parallel, and you show all possible things that work for solving the problem, right? And the cool thing, again, I think it's not a surprise that it is extensible. AI. Let's talk briefly about AI. Lean enables verified AI, right? This is really important because large language models, I think by now everybody agrees they are really powerful tools, but they hallucinate, and a small mistake in a math proof, right, invalidates the whole thing. And it's amazing, especially if you want a result that there is a bogus proof in some textbooks. It's impossible to convince the LLM to give you the right one. It's like it's burned in their memory that's the bogus proof, and they keep giving you the wrong proof over and over again. I mean, it's really annoying. But with proof assistants, we believe they are the antidote for hallucination. Proof assistants can also help AI. Right? You can use proof assistants to generate syntactic data that's correct by construction. Later today, Sunho he's leading a project called AI Lean at Amazon, and he will talk about how he's using Lean to generate syntactic data. He has really great results. He's using Pentagraph by Lenny Aniva from Stanford. Pentagraph is a tool for extracting data from Lean repositories like MathLib. Pentagraph is getting really popular. I know a few startups that are using Pentagraph now. But AI can also help proof assistants, right? You have many groups building AI for Lean, from Caltech, OpenAI, Meta AI, Google DeepMind. Claude 4 is fantastic on Lean code. It's really good at explaining, creating proofs. Even the system cards that the manual they release comes, the latest one has a Lean example inside. But it's impossible to talk about AI without talking about Alpha Proof, right? Alpha Proof is this AI that Google DeepMind built on top of Lean that got a silver medal at the International Mathematical Olympiad. The IMO is really hard, right? Many of my colleagues did not thought this was possible. It's crazy, but even Turnstile, I think he did not think. I mean, we are in a committee of an open source competition, and I think he was preparing his talk for the first edition of this open source competition for the IMO. He was preparing his talk. He did not expect that Google DeepMind would release these results a few days before his talk, right? And now they also have this new initiative called Formal Conjectures, where they're collecting many open conjectures in mathematics in Lean, right, and make them available on their GitHub repository. Auto-formalization is also a key area, lots of activity there. It's the process of converting natural language to formal language automatically. And last week I was joking with Sebastian that was really eventful week. On top of all these things, Turnstile, there was this result. I was casually listening. I couldn't attend the Big Proof seminar, and Bavik was giving a talk. I was watching online the talk. Bavik had many contributions to Lean, MathLib. He verified results that before they were published. I mean, he's a student from Chingowers, that's a Fields medalist. He was part of the Alpha Proof team. Last week, he was giving a talk about a new result he was formalizing that relies on a result by De Bruyne, a result from the 60s. And this result was auto-formalized automatically by a new system that Christian Zagadi is building at Morph Labs. Their system formalizes the paper, right, in Lean, and Bavik just used the results. I was blown away. I think nobody was expecting that this was going to be announced during Big Proof. Before we wrap up, I like to tell a little bit about the Lean Flow, right? Sebastian and I launched the Lean Flow in August 2023. It now has 19 members. The mission is to improve the scalability, usability, documentation, and proof automation in Lean. We also want to be self-sustainable in August 2028. It should be like the Rust Foundation. Right now, we rely on philanthropic donations, and we are really grateful. I think it would be impossible for us to run the Lean project without the donations and the whole team now. By numbers, I think our productivity increases a lot. Now we have one release almost every month we release a new version. More than 4,000 pull requests have been merged since the beginning of the flow. We have public roadmaps. Lean appears in many venues since the flow started, 3 times at the New York Times, Quanta, Scientific American, and so on. The release 422 will celebrate the 2nd anniversary of the flow, and we are packing many cool things, like the new compiler, the module system that Sebastian is working on, and many other features. I want to finish also telling you a little bit about CSLib. CSLib is a new initiative. The goal is to be the MathLib for computer science. The steering committee, Sarat and Clark, I think they're the main driving forces. Sarat is Google DeepMind and UT Austin. Clark is at Stanford and Amazon. And Jason Rose and myself are also helping, right? And the goal, the mission is to have a foundation for teaching, research, and verification efforts, including AI-assisted ones. How can you contribute? You can contribute in many different ways. You can contribute to MathLib, right? You can join the Zulip channel where the community gathers. If you care about machine learning kernels, you can contribute to KLR, right? You can talk to Daniel. Daniel is here. If you want to contribute to a large formalization project, contribute to Fermat's theorem. I mean, there are people all over the place. Kevin tells me that sometimes he creates issues for each lemma that has to be proved. He comes back and people proved everything for him. I mean, if you create your own project, we'll show up in Reservoir. We have more than 4,000 there. You can try Lean live on your web browser without installing anything. And you can also support the flow with funding, partnerships, and advocating the project. Advocacy is super important for us. Well, I hope, I try to repeat over and over again. I will say it one last time. Lean is extensible. You can build your own system inside of Lean. You can leverage every single piece, like the folks working on Veil did, like Ilya and Vladimir did, right? You are going to leverage the proof automation we are building, not just us, but also our collaborators in Stanford, CMU, and so on, right? You're going to leverage all the IDE, the tooling, the build system, everything, the documentation, right? All the books the community are writing, right? Explaining how to use the system. This is just the beginning. The progress now is accelerating. We truly believe the math community is changing, the MathLib community is changing how math is done. And it's not just about proving, but going beyond your cognitive abilities. Thank you very much. You can get the slides on the QR codes. Thank you.
We have time for a couple questions as well. Okay, Adam's already there. Make sure to introduce yourself as well, everybody, and let's start.
Hey, Adam Japala from MIT. So, as I understand it, despite the examples of like program verification uses you highlighted, the vast majority of uses of Lean are still in math, which has this funny property that though we know math underlies engineering, what mathematicians do in some sense is sort of more similar to professional athletics or something, in that it's kind of part of the point of the exercise that everything you do is really hard, otherwise you're not going to spend time on it. And if you're looking at program verification instead, you're dealing more with lots of really small, individually boring details that you have to thread together in the right way. And this difference can potentially have interesting consequences for the design of formal methods tools. I think in the verification examples you showed, they were all relatively short but interesting programs. Mm-hmm. And I wonder what you think about what might be different in the evolution of Lean to support something like verifying thousands of lines of code written in some language that's not the native functional programming language of Lean.
Yeah, this is a great question. We really care about that. We have two initiatives for our year 3 roadmap. We have two initiatives to push forward in this direction. One is the WebAssembly. I mean, Joachim Breitner, I saw it. He works for the Pro now, Joachim. And Joachim wants to do WebAssembly in Lean, to do all the verification. This is one initiative. The other one, Cameron Zorek, he's the guy that implemented Rosetta 2 for Apple. He works for the Pro now. And he also works on Apple hardware. He wants to do a front end for Verilog, for Lean, and to push as hard as possible. He believes that we can, he's a no bullshit guy. He wants to make sure, he believes the best way to make Lean self-sustainable is hardware, because he knows the people at Apple that do hardware verification. He said, these people care about correctness, because if they have a bug, screws up everything. I want to make sure that we can scale Lean to really, to real hardware designs. That's two directions we are pushing. And of course, at Amazon, we are pushing a lot in software verification. That's another source. I fully agree with you. I mean, your message exchange is saying, I have doubts about scalability. We have too, but we are going to work super hard to make sure that we'll succeed there too. But you're right. I mean, there are different kinds of problems. One, the complexity, is different kinds of complexity. One is just sheer size, and the other one is really mathematical. I think I liked your term athletics, right?
Thank you.
Yeah, welcome.
Next one. Hi, Robert Rand, University of Chicago. Early in your talk, you mentioned that you need to have this small trusted code base because if you're going to give it to an LLM, for instance, it will exploit whatever it can exploit to prove the thing that you're trying to prove. But as I understand it, Lean can run arbitrary code. It's not like the rock proof assistant where, you know, in order to actually execute something, I need to export it into OCaml and then run whatever comes out of that. So is there a way to make, you know, Lean such that I can trust just giving it to an LLM and let that LLM run stuff on it?
Well, you can trust the proofs, right? The proofs that are built, you can be independently checked. Of course, in Lean, you can write programs that you cannot verify properties. We have a keyword that allows you to write unsafe code. That's critical for writing the parts of the proof assistant that you want to make them super fast. And we use unsafe features. And whenever you use unsafe feature, the primitive is like an opaque primitive. You cannot reason about it. It's like this trade-off. Whenever you use unsafe feature today in Lean, we cannot reason about it. Of course, many people in the Lean community have dreams that one day we are going to have a low-level IR with the semantics, and you can write the unsafe features in this IR, and you're going to be able to reason. But today, yeah, we cannot, right?
So is there a version of Lean where I can just exclude all the unsafe behavior and just, you know, to provide that as an input to the LLM so it can?
Oh yeah, no, keep in mind, when you can provide unsafe features, you're not going to be able to prove anything about them. But you can. I mean, in Lean, you can trace back. If you're using a unsafe feature, if you're using an axiom, keep in mind that that's lesson that Kevin Buzzard had is true for us, for code too. Now code is data in Lean. You have APIs to traverse. You can check if you're using a funky axiom. You can write a program that will check if you're using a specific axiom, if you're using unsafe feature, which functions are used unsafe feature. You can write a program in Lean that will give you all this information, right? The same way Kevin says, math is data, Lean code is data too that can be manipulated in Lean.
All right, thanks.
Yeah.
All right, I think that's it. Thank you so much again. Let's thank Leo for the great talk.